Infrastructure is the domain of the civil engineer. It is civil engineers who design, build, and maintain the public works which constitute the physical framework of the civilization we enjoy and often take for granted. In the course of the 20th century, we have seen achievements in this field that our ancestors never have imagined. As the momentum of our technical success carries us forward into the 21st century, it is time to review where we have come from, what we have learned, and where we are going. The Alps loom like snow-capped giants, barring the way to travelers between the Italian peninsula and the world to the north. These mountains and the roof of Europe are typical of the challenges which civil engineering was created to overcome. The world's first modern mountain tunnel came into being at Montsuni Park, born in the railway building frenzy that sprang from the Industrial Revolution. Dynamite and rock drills used in the Alps in the 19th century launched a new era in the art of tunnel making. Today, the St. Gotthard, the world's longest highway tunnel, runs 16 kilometers through the Swiss Alps. The evolution of tunnel technology from the 19th century to the present has not been easy. In mid-20th century Japan, the Tana Tunnel and others were built by what was at the time the most up-to-date technology. But the operation was still labor-intensive, plagued by floods and the ever-present danger of collapse. Elaborate scaffolds were devised to keep the ground in place, but structures of wood and steel can only provide support at certain points, and the trouble may begin at any point. Rock is typically fragmented, and the cracks are often filled with sand and clay. Under the influence of gravity and seepage, these work loose. A piece of rock falls out, and then another. Disintegration is underway. In 1940, an Austrian tunnel engineer, Ladislaus Ravsevich, became known for a new idea. The principle of the new Austrian tunneling method, or Natm, was to transform the fractured surface of the tunnel into a continuous self-supporting arch. Wet concrete is sprayed over every inch of the walls and ceiling of the tunnel. The concrete lining prevents the escape of the bits and pieces, which, if they're kept together, give the arch its natural strength. The concrete fingers of the lining reach into cavities, uniting rock and concrete in a single purpose. Successful technologies spread rapidly in a shrinking world, and widespread use improves them. Japan is largely mountainous. Tunnels are links in its communications infrastructure. The Austrian method was effective for long, large tunnels needed for bullet trains and highways. Timing was crucial to the method's success. After the initial excavation, the concrete lining had to be applied to the raw surface as quickly as possible leaving no time for rock to start deteriorating. The stability of the lining is enhanced by using iron rods called rock bolts. The rock is drilled to receive them. Bolts are cemented deep within the rock and serve as anchors. The rods and plates keep the concrete sheath secure and the tunnel intact. Natm was a technical revolution. Kanmon Strait divides the island of Kyushu from Honshu, Japan's main island. Linking these islands was the job of the world's first undersea tunnel, completed in 1944. Lessons learned here let Japan undertake the daunting task of a tunnel linking Honshu with the northern island Hokkaido. The trigger was the loss of a ferry boat with over 1,000 lives in 1954. Construction of the Seikan Tunnel began in 1971. Surmounting many difficulties, including earth faults, the Seikan Tunnel was finished in 1988. Honshu and Hokkaido were joined by the longest tunnel in the world. Technology developed for the Kanmon and Seikan tunnels played a major role in building another tunnel, half a world away, the Eurotunnel under the English Channel. This is the breakthrough, the final moment. Until this moment, Britain, the island, was odd man out in Europe. Now, symbolically at least, that special status has come to an end, thanks in part to this remarkable machine. The Eurotunnel now links Britain to the continent of Europe. Over 15 million people currently take ferries or hovercraft each year. The channel, as it's called, was born of the conjunction of political imagination and modern engineering. It's certain to become a major link in the infrastructure of a new united Europe. June 1993 saw the first test run of a train from France to England. Eventually, London and Paris will be just 3 hours apart. The tunnel runs below the ocean floor of the English Channel for 38 kilometers, though its overall length is nearer 50. It's strictly for railways, and when it's in full service, will run 10 trains every hour. The car trains will carry trucks of up to 40 tons. The construction of the Eurotunnel took a mere 3 years. This was in part due to favorable ground conditions and in part to technology. The dream of a tunnel under the English Channel has been around for at least a couple of hundred years. In 1876, Queen Victoria and Napoleon III agreed to make it happen. Drilling was done on both sides of the channel. One can still see the remains of this short-lived enterprise near Folkestone. Techniques used then for drilling through chalk were primitive precursors of those we use today. The machines themselves were steam-powered prototypes of the ones used in the 1990s to excavate the channel. Politics halted this project after a brief 2 kilometers, and the dream lay dormant for another 100 years. In the modern world of the 1980s, 9-meter diameter Japanese machines played a part in unifying Europe. 11 of these tunneling machines were used to dig the Eurotunnel. France and Britain mobilized their engineering power. Vertical pits were dug on both sides of the channel. From the bottom of the pits, tunnel machines began to dig horizontally. The rotating cutter is at the front end of a cylinder of steel which encases and protects the whole machine. Behind the cutter, an apparatus assembles the concrete tunnel lining while excavation proceeds. When a ring of concrete is complete, a series of hydraulic jacks push against its rim, and the whole machine advances. It's called a shield machine. It builds as it drills and trails the finished lining and its own support surfaces behind it. This is the shield construction method at its best. The main problem encountered by engineers building undersea tunnels is water seepage. In the case of the channel, the geology was benign. A stratum of blue chalk running 40 meters below the channel floor resists water penetration. But the layer is only 20 to 30 meters thick, so careful subterranean navigation was essential. The shield machine is not suited for drilling in complex or unstable strata, but it is ideal for blue chalk. Sometimes the machine dug 50 meters a day, 3 times faster than expected. On an average day, 20,000 tons of material were pulverized and carried to the surface, enough to fill 2,000 dump trucks. The construction of the lining, of course, had to keep up with the pace of the excavation. The 8-ton concrete segments of the cylindrical wall were automatically applied to the wall of the tunnel. The tunnel is almost 8 meters across. Together, the blue chalk layer and the latest shield construction technology let the tunnel under the English Channel be built in record time, 50 kilometers in 42 months. The shield method idea was devised in Britain in 1818 at the peak of the Industrial Revolution. The first tunnel built with this method goes under the River Thames. The inventor was a creative engineer called Mark Brunel. That first tunnel is still part of the infrastructure of the London Underground. Wapping Station still uses the vertical shaft from the bottom of which Brunel's machine bored below the river. At the time, many people thought that the ground below the river was too unstable to permit construction of a tunnel, but Brunel, with his invention, proved them wrong. His tunnel has survived for more than 150 years. Mark Brunel owned a lumber mill. It was there that he found the clue which led him to invent the shield machine. Brunel was intrigued by the little holes which are often seen in old lumber. The holes are made by shipworms. They're mollusks related to clams. At that time, London docks were full of ships from all over the world, and their hulls were full of worms. These creatures, just millimeters thick, may grow to be tens of centimeters long. They bore into wood using their tiny shells to do the drilling. As they progress, they secrete a substance which coats and toughens tunnel walls against compression and collapse. The white substance here is a shipworm's tunnel lining. The notion of boring and building simultaneously inspired Brunel. The walls of the tunnel he conceived were not concrete, but brick, and construction was primitive by modern standards, but this is how it began. Mark Brunel was born in France, but came to live and work in England. His homelands have now been linked by his invention, inspired by a clam, the shield construction method. The largest and most advanced shield machines are now being manufactured in Japan. This one is 14 meters in diameter and will weigh 3,000 tons. Meanwhile, a tiny sensor controls its automated functions, its nervous system. These sensors will be its eyes and fingers for watching and feeling. The activities of the giant automatic wall constructor are directed in accordance with information delivered by laser sensors. They guide the assembly to a tolerance of less than 1 millimeter. Sensors will be stationed at over 100 points on the machine. The cutting blades, teeth, determine the speed of excavation. Most of the soil in Japan is a complex variety of strata, and cutters have to cope with that variety. Blades are made of exceptionally durable materials like tungsten carbide and cobalt steel. Shield machines are now being used extensively in Japanese cities for subways and sewage systems. Tokyo Bay is today a showcase for the most up-to-date developments in infrastructure technology. A 15-kilometer overpass is being built between Kawasaki and Kisarazu. A 5-kilometer bridge will link the Kisarazu side to Kisarazu Artificial Island. From there, the road will pass for 10 kilometers through a tunnel under the ocean to Kawasaki. Halfway along the tunnel is a second artificial island. At that point, a vertical hole 100 meters in diameter will ventilate the tunnel, exhausting the fumes of the 64,000 vehicles which will pass through daily. This huge hole will serve initially as a base for shield machines used to build the tunnel. The giant excavators are already dwarfed by the structure they are helping to create. From the bottom of the pit in Kawasaki Island, shield machines will drill in both directions until they meet their opposite numbers beneath the ocean floor. 8 machines will be employed. They are 14 meters in diameter. Each of the tunnels will carry a 4-lane highway. Digging underground is not the only way to make a tunnel. Some are manufactured on the surface. These bleak concrete structures that look like a series of crude warehouses are in fact components in another kind of tunnel for Tokyo Bay development. Each unit is 130 meters long by 40 meters wide. Each is a section of concrete duct sealed temporarily at either end by steel plates. Strung together end to end on the seabed, they'll carry a 6-lane highway between 2 artificial islands. 4 are in place already. The 5th is on its way. The caisson is suspended from a pontoon frame just below the surface of the water. The whole system is towed to the site by tugboats. Like the shield machine, this method was invented in the 19th century. The first tunnel of this kind constructed in Japan was built in 1944. This method is only suitable in comparatively shallow water. The box tunnel under construction will consist of 9 concrete sections with a total length of 1,200 meters. It will become part of the Metropolitan Expressway. The crew is now lowering tunnel section number 5 into the grooves prepared for it on the seabed. It will connect with the already submerged section number 4, where another crew waits to receive it. Engineers at the surface use sonar to monitor the precise placement of the caisson. Shifting ocean currents could be disruptive. We are now driving down the part of the tunnel which has already been assembled. The receiving crew is at the end, waiting to tie section number 5 into the system. In the center of the picture we see one set of the hydraulic rams which will draw the new section into its final position. This is a graphic preview of the docking procedure. After the units are in place and sealed together tightly by the pressure of water against them, the water between the temporary bulkheads will be drained out. The hydraulic rams are now drawing Section 5 into position. The capacity of the rams is 400 tons, but the caisson weighs 50,000 tons. Docking had to be done making precise allowance for the current and the seafloor profile. Section 5 is now in place. Valves are open to allow the water to drain from between the bulkheads. The lowering of the new section from the surface began 10 hours ago. The tunnel is now 130 meters longer. The British economy boomed in the 19th century, putting pressure on her transportation system to expand. In the race for prosperity, bridge and railroad construction engineers overcame obstacle after obstacle. But the efficient extension of the British rail system into Scotland was interrupted by two formidable barriers, the Firth of Forth and the Firth of Tay. These great arms of the North Sea stood in the way of economic growth. Britain's daring response was to build a bridge over the Firth of Tay. The bridge over the Tay was the crowning achievement of the Age of Iron, 3 kilometers long. In 1878, it was the world's longest bridge. It took 7 years to bridge the Tay. Then one night, less than 2 years after it was finished, a storm slapped it down. A train plunged off the broken end. 75 lives were lost, the worst accident in railroad history to that time. Local historian Christopher Dingwald.
Well, here we are at the Tay Bridge. And what you see is the remains of Thomas Boucher's old bridge alongside the new bridge. All that you see of Thomas Boucher's bridge are the bases of the old piers or pillars which supported the bridge, which just stick up above the water.
These were the foundations on which engineer Sir Thomas Bouch raised his cast iron piers, a popular building material at the time. However, the official inquiry blamed the disaster on the weakness of those piers. Suspicion focused thereafter on cast iron as a material for construction. But what was the alternative? Henry Bessemer had recently devised an economic method for mass-producing steel. The British government was hesitant at first, but after many tests, it endorsed steel as a material for construction. The bridge over the Firth of Forth was built 11 years after the Tay Bridge disaster. This bridge now became the largest in the world, built entirely of steel, 51,000 tons of it. Some critics of the day complained that the bridge across the Forth was over-designed, but the Tay Bridge collapse was still fresh in people's minds. The bridge over the Firth of Forth celebrates the advent of the Age of Steel. The Brooklyn Bridge spans New York's East River. Built in 1883, it is a landmark of suspension bridge technology. Continuous improvement of suspension bridge technology since then has resulted in a series of bridges spanning greater distances, advancing from 500 to 1,000 meter spans in 50 years. The Seto Ohashi Bridge, Japan. In Japan, a land of islands, the evolution of suspension bridge technology has been exceptionally rapid. The crowning achievement of that technology is being built over Akashi Strait from Kobe to Awajishima Island, almost 2 kilometers long, 500 meters longer than the current world record. Its cables must support 120,000 tons. The girder can stand winds of better than 320 kilometers an hour. This is one of the 2 towers. Each tower is built up of 30 hollow steel blocks piled one above the other. The finished tower must be vertical. Precision is essential. The blocks must fit perfectly. No bumps or gaps, however small, will be permitted. The steel blocks were manufactured in 13 factories throughout Japan. These blocks have just been built. End faces are still uneven. Now begins the all-important work of milling them smooth. The work is done at night, when distortion of the block due to temperature variations at different points is minimal. Work will begin when the 8 sensors read within 1 degree Celsius of each other. Work began tonight at 10 p.m. Using this rotary cutter, the worker shaves the surface absolutely flat. Each block is processed by a single person to ensure consistency. The job requires a high degree of skill as well as the right machinery. The aim is to finish before morning, when temperature variations could result in slight but critical distortions. The milling is finished. It's time to put two blocks together to see how well they fit. These blocks are carefully aligned, lying on their sides. A feeler gauge tests for gaps. The metal strips are 1/100th of a millimeter thick. There are 500 test points where the two blocks meet. If the feeler gauge can be slipped in at more than half of these, the fit is unacceptable. Precision in its foundations is just as important as precision in the towers. Fast currents made use of the world's heaviest seabed excavator, 200 tons, essential. A submarine robot is used to check the flatness of the seabed. Caissons 80 meters in diameter will form the tower foundations. Extraordinary precision is demanded of the surface on which the towers will stand. The surface was polished for 3 months to bring it to a mirror finish in preparation for the assembly of the towers. Construction of the towers is now well underway. Each block weighs close to the 160-ton capacity of the crane. 280 meters above sea level, the wind is a constant hazard. Its speed and direction must be closely watched. The crew at the top of the tower help guide the block into its position. At this point, human judgment and human skill are indispensable. The moment of truth. Will the perfect fit be realized? It must be under 5 millimeters. These guide marks must line up. The block is finally in place. 10,000 bolts will follow. The error, less than 1 millimeter. The feeler gauge confirms success. Now the twin towers wait in the Akashi Strait for the 120,000-ton bridge to be completed in 1998. July 1940, the opening of the Tacoma Narrows Bridge. This bridge across Puget Sound was built more than half a century before the towers in the Akashi Strait. Engineers learned from past mistakes, and the disaster of the Tacoma Bridge provided a terrifying lesson. 4 months after it opened, the so-called ribbon over the Sound was blown apart by a wind of only 68 kilometers per hour. Why did it happen? Aerodynamic specialists in civil engineering eventually found the answer. A succession of low-pressure eddies roll across the bridge above and below, but the eddies above are out of step with the eddies below. A rolling pull above is followed by a rolling pull below, resulting in a twist. The twisting is rhythmic, and the rhythm is self-reinforcing. Orange areas represent the force exerted at different points and at different times as the wind streams across the surface. Before they designed the Akashi Bridge, the Honshu Shikoku Bridge Company made a careful study of the winds in the Akashi Strait. The record shows that in 1964, when a typhoon cut across the Seto Inland Sea close to Akashi Strait, it generated winds up to 183 kilometers an hour. It was agreed to design the Akashi Bridge to withstand winds of 281 kilometers an hour. The design was tested in the world's largest wind tunnel. A 40-meter-long model was used for the test. It copies the Akashi Bridge in every detail at 1/100th the size. The focus of attention is the girder. After years of debate, the traditional truss type was chosen for the job. The truss girder has a long history of success and is resistant to twisting. Much of the wind will simply pass through its lattice. But how will it behave in winds of 281 kilometers an hour? "36 powerful fans put the question to the bridge. The wind speed is gradually increased. It has now reached the 281 kilometer an hour maximum that the bridge is required to withstand. And there's not a trace of oscillation. The speed is increased to 335 kilometers an hour. Only here, at a speed beyond anything known in nature, do the fatal oscillations begin. The girder has passed the examination with flying colors. The cable supporting the Akashi Bridge will be more than 1 meter in diameter. It begins life as a wire 11 millimeters thick, which is reduced in size still further by cold drawing. No heat is applied, just several tons of pressure. From 11 millimeters down to 5. Its tensile strength has been virtually doubled by squeezing out the gaps in the crystal structure of steel. Each 5-millimeter wire is more than 4 kilometers long. 127 are bundled together to make a strand. 290 strands will be strung over the channel one by one, and they in turn will be bundled to make the cable. The construction of cable made from wires in parallel rather than twisted wire rope was first used in the Brooklyn Bridge, New York, in the 19th century. That invention spurred the evolution of suspension bridge technology. The culmination of that evolution is the bridge that will soar over the Akashi Strait. Cities and their infrastructures grow in affluent times. The growth of New York in the early 20th century was phenomenal. Most of its skyscrapers, bridges, and highways were built before 1930. We take our physical surroundings so much for granted that the process of aging comes as a surprise. In 1988, New York suddenly closed the Williamsburg Bridge. A crack more than 80 centimeters long was found in the girder. The cables were dangerously rusted. Part of a cable was actually broken. The flag unit in the city of New York monitors the condition of the bridges on which the city's life depends. Red flags indicate areas in need of immediate repair. 2,000 of these have been identified. Yellow flags call for repairs in 2 years' time. Of these, there are more than 7,000.
Many of these are on the Williamsburg Bridge, indicating the large number of flags that we have on just one particular bridge.
As the process of decay continues, red flags replace the yellow ones. The number of red flags has increased threefold in the past 4 years. Dr. Boyardar Zyenev is with the Department of Bridges of the City of New York.
And bridges over